In our last lecture, we started dealing with numerical analysis. And we will continue with local analysis. That's the other course I'm teaching, local analysis. And we are going to continue that in this lecture. So, fine. What I want to say, nothing. I hope there will be no sirens, but otherwise. Okay. So let me start from the point that we have stopped in the last lecture. We started with the area equation, which is that, and we want to analyze this, the behavior of this equation as x goes to infinity. And since this is an irregular singular point, we have no way to expand it in a power series or something. Power series is not going to work. Neither Taylor series nor Frobenius and others, they are not going to work. We must do something else. And the trick is to write y as e to the s, right? And then we obtain the equation s double prime plus s prime squared equals x, which is as complicated as this one because of the law of conservation of difficulty. Still, we can do a lot of progress if we will replace it by the the asymptotic sign, meaning that we want s double prime plus s prime to be asymptotic to x at x goes to infinity. Right? This is the definition of the problem. Okay? Now, we can do that. Okay? And now we can implement the dominant balance technique. So let me, because we already did that in the last lecture, let me try to cut a few corners and to write, to assume that S is, what letters I want to implement here. Let me see. Okay, I'm assuming that S is actually S plus C plus D, okay? Unknown function of X. But I assume that each of them is negligible with respect to the former one, so I assume that D is negligible with respect to C, which is negligible with respect to S, at x goes to infinity. Okay? And this implies that the equation is maybe written, okay, I used S twice, right? So don't cancel it. It's okay. Let's call it F. So F, D is much smaller than C, much smaller than F. Okay? Now we can write it as F double prime plus C double prime plus D double prime. This is S double prime. Plus F prime plus C prime plus D prime squared equal X. Not equal, sorry, is asymptotic to X. Okay? So what I have here, I have F double prime plus C double prime plus D double prime plus F prime squared plus 2 F prime C prime plus 2 F prime D prime plus C prime squared plus D prime squared is asymptotic to X. Good. just open it. These are the terms. Okay, now, who is the most dominant term in all this? That we have analyzed it last time, right? First of all, we always assume that C prime and D prime.
Aren't you missing the C prime, D prime? It's negligible.
Yeah. Okay. No. Let's write it. It's both of you are right. Right. Okay. So I always assume that this is true, and of course this is true also, and this is true also, right? Okay. So who is the biggest term? Right? So I can neglect this one and this one with respect to that, and all these guys with respect to the f prime squared, right? So the only question is, who is bigger, f prime squared or f double prime? And last lecture we analyzed this question, and we find out that the f prime squared is the biggest, is the dominant one, right? This is dominant balance. So dominant balance, if I just okay, let me try to. I would like to keep it. Okay, so clearly from these three, the f double prime is the dominant. From all these, how much there are here? 6, I guess. F prime squared is dominant, and they should be asymptotic to x. And now we have the following. We have 3 options that we have analyzed last time. I did it, right? Yes. So we may try this equals that, we may try this equals that, and we may try this equals that, and we figure out that this was the right choice. Okay? So first of all, we are saying that f prime squared is asymptotic to x. Sometimes I'm writing equal to, but you have to assume to understand that it is asymptotic. And I'm not writing every line that this is as x goes to infinity, but there's the only meaning of that. So f prime is asymptotic to plus minus square root of x. So f is asymptotic to plus minus 2/3 x to the 3/2. So f double prime is asymptotic to plus minus 1/2 square root of x, right? That's the leading term. And if this is the leading term, so we are saying that f is asymptotic to what? To f, so plus minus 2/3 x to the 3/2, right? Which is correct. And we want to write that y, which is e to the s, is asymptotic to e to the plus minus 2/3 x to the 3/2. And this, as I tried to convince you last time, is not necessarily correct. This is what's called the controlling factor. It's not necessarily correct because if function is asymptotic to another function, it doesn't mean that the exponent of this function is asymptotic to the exponent of the other function. This is true only if if the difference between this s and z is something that goes like 1/x or goes to 0 as x goes to infinity. And I mean, I don't know what I have here, so I don't know what will not here. Okay? Good. Next step. Next step is now, so I decided, now I have to keep, from this equation, I would like to keep all the terms that are, what will be the next order? Okay? So I have this f prime squared, which is, what is f prime squared? S. Yes. So f prime squared is x. Okay? And we have the x here. And they will cancel each other. That's the meaning of what we did in the first step. Now, what will be the next? Okay, from these three, I can still say that f double prime is the dominant one, right? Because by definition, this and this are negligible with respect to f double prime as x goes to infinity. Okay, so I have this, and now I would like to take from these guys the biggest one. Who it is going to be? The f prime c, right? First, because clearly c squared is smaller than fc, and of course d is smaller than c, so it will be the f prime c. So I will have this equation plus 2f prime c prime is equals to x, and the x cancels out. So what I get is f double prime, but what if is f double prime? I know it's plus minus 1 over 2 square root of x. That's f double prime. Okay. Plus 2 f prime c, so plus minus 2 square root of x c prime is, okay, I cannot write asymptotic to 0, so I will write equal to 0. I have to move it to the other side. Okay? And this implies that c prime is minus 1 over 4x, just by algebra. So c is minus 1/4 ln x. So c double prime is 1 over 4x squared. You see? Good. So now I know that I have here minus c. Now what is c? 1/4 ln x. So this implies that what I have here is x to the minus 1/4. That's the next term. Okay? Now, you have to tell me, so I know that this term gone with the x, and I discovered that this term and this term cancel each other. Okay? So now what will be the next, what will be, if I want to calculate the next order. What will be the next order?
It depends on how much bigger f from c, if like f over c in contrast to c over d.
Okay, let's see. From these two, I know that c double prime is much larger than d double prime. So I will keep only the c double prime, right? So I will keep only c double prime, which is 1 over 4x squared. You see? Okay? Now, clearly, I have, okay, so now I have plus 2f prime d prime. So if d prime times 2 f prime. 2f prime is plus minus 2 square root of x. This is 2d f prime d prime. Okay? This is this one. Now, c prime squared, let's write it. So I have plus 1 over 16x squared. You see? That's a c prime squared. Now, there is no point in keeping d prime squared when I have c prime squared, because d prime squared is clearly much smaller. And c prime d is again much smaller than c prime squared. So this is what I have. So this should be equal to 0 again, and this implies that d prime times 2 square root of x is 1 over, first of all, I don't like something here with the plus and the minuses. It's not important. Okay. We are only interested in the order of magnitude. Okay. Maybe I have a mistake here with the plus and the minuses. I think the minus 1/4 plus 1 over 16, right? How much is that? It's 1/4, it's 5 over 16. 5 over 16x squared. Okay, so d prime is 5 over 32 times x to the 5 half, because of this square. And this implies that what is d? I have to integrate that. Right, so what's the integral of x to the 5 half? Minus 5 half. Right, it's minus, it's 2/3, right? X to the minus 3 halves times 5 over 32. Okay, so what I have is minus, again up to a sign. Okay, here I have minus plus, so here I have plus minus, so here I have plus minus, something like that. 10 over, okay, so 5 over 48 x to the 3 halves. Okay, can you see that? And this is very good, because now we say what we have here. What's the extra term? S is this minus z. This was F, this was C, and what is D? Plus minus 5 over 48 x to the 3 halves. Now I know that this is actually a really asymptotic relationship.
How do you know where to stop? How do you know if you shouldn't continue to like plus E plus...
No, because all the other terms, if I have now C, D, E, then E is negligible with respect to D as x goes to infinity. So if D is going to 0, then E should go to 0. So all higher order terms must go to 0. Right? I can't have the next term ln x or something.
So you stop when you have a
You stop when you have
to 0?
what?
When you get a term that goes to 0?
When you have something that goes to 0 at the limit x go to x naught, which is in this case it goes to infinity, then you can stop. And you can say, okay, I have shown that this is indeed y is asymptotic to z as x goes to infinity.
And if it goes to 0, you don't need to include it?
When x goes to 0?
No, when like d went to 0, so you didn't include it in the y?
Of course not. Right? Because it gives you something which is... I mean, what people want to see is that. Okay. So this is essentially the way one can do local analysis at the vicinity of an irregular singular point. Now, the interesting point is I didn't bring a graph to show you that, but if you look at the book, right, this is, if you take you remember last time we showed what's happened close to 0. So we have a Taylor series converging for every x. But if you want to expect to find the right number at x equals 5, say, you have to take like 30 terms. I don't remember how much, but something like that. I mean, 10 terms. Here, this is very good approximation from infinity to 1. I mean, it's very close to the right, it gives you very closely the correct behavior, not at the vicinity of infinity means when it's much larger than 10 to the 6. No, it goes it has a deviation of a few percent at 2 or 1. Okay, so this is a great approximation, and the moral is that close to an irregular singular point, of course you have no order or proven mathematical procedure, but the actual analysis is much easier. Yes?
Can I do the same analysis for minus infinity?
We will, it's an excellent question. I mean, I intend to speak about it later this lecture. Okay, fine. So, however, I would like to continue to ride on this horse of Airy equation in order to show you something else. Okay? And this is, now let's, okay, so we have arrived at this point, we are very happy. Now, and we've actually calculated the next correction, which is that. Okay? Now I can continue, as you suggested, D, E, whatever, F, D, C, D, E, G, right? But as you see, it will be more and more complicated, and I will have to take care of more and more terms. Instead of that, I'm trying to now to calculate all the rest of the terms at once. How do I do that? You see them? Okay. What I would like to do is to write y is equal to x to the minus 1/4 e to the plus minus 3/2 2/3 x to the 3/2 times w. This, of course, is completely legitimate because I didn't specify w. You see? And now I would like to obtain an expression for w as an infinite series. So what I would like to do, exactly what we did last lecture. Close to 0. I want to do the expansion close to infinity with an infinite series, and I will use this series in order to explain you what is going on at infinity, or how to use such a series. To facilitate our work, again, it's very important to not to drag yourself into the algebra or whatever we call the calculus. Instead, having, keeping the general perspective of what we are doing here. So, I am going to say that A is e to the plus minus 2/3, right? X to the 3/2. These are just preparation for the calculation, right? So what is A prime? A prime is plus minus square root of x e to the plus minus 2/3 x to the 3/2. And what is A double prime? Which is, of course, plus minus square root of x times A. What is A double prime?
Sum of.
I can take the derivative either here or here. If I'm taking the derivative here, it just brings me another factor, so it will be x times e to the plus minus 2/3 x to the 3/2. And I can take the derivative here, in which case I will get plus minus 1 over 2 square root of x times A. Right? So I can write. Next, I would like to define B as x to the minus 1/4. What will be B prime? B prime is minus 1/4 x to the minus 5/4, and I would like to write it as minus 1 over 4x times B. You see? And B double prime will be 5 over 16 x to the minus 9 quarters, which is 5 over 16 x squared times b. Okay? Having this in mind, let's go to the back to here. And I can write y as a times b times w with these definitions of a and b. And I would like to write now the equation what is y double prime. Can you help me? How do I take the second derivative of multiplication of three functions?
Slowly.
Slowly. Okay. So I can take the second derivative here, or here, or here, or two times this and that, this and that, and this and that. Okay? So what I have is a second derivative is what? Is x. So it's x times y, because I have a, b, w, plus minus 1 over 2 square root of x times y. This is a double prime b y, b w. Now let's take the second derivative of b. So we have plus 5 over 16x squared a times y again. And we have also now a and b. A and b, this will give me plus 2, first of all, 2a prime b prime. So the a prime will give me, I have plus minus square root of x, and from the b prime I have minus, so it will be minus plus 1 over 4x. This is again times y, a, b, w. Okay? Now we have to take the terms that include derivatives of w. So we have a, b, w, double prime, plus a, 2a prime, w prime. So it's plus minus 2 square root of x a, b, w, plus 2b prime, w prime, which is minus,
You forgot prime.
minus 2b prime. So I have minus 1 over 2x a, b, w prime. Okay? Now, this is w double prime. And this should be equal to what?
X, Y.
X times y. Good. And now we can see that. What you can see here.
The second term cancel out.
Where is my red? I didn't bring a red. No? Okay, no red. Sorry. So I'll use the green. Okay. So first of all,
You
this
want
one, oh, that's fine. This one cancels with that one. Okay? Next. Who else cancels?
The second term and
The second and the fourth, you see? The second term cancels the fourth term. Okay, and what remains? What remains is a very interesting equation for w double prime. So I have w double prime times ab. now that I cancelled all these guys, I can also divide by AB. Okay? So I have W double prime minus 1 over 2x W prime. This is from here. You see? And I have this one, again, if the y divided by AB is W, so I have plus 5 over 16x squared times W. Okay? And this is
No, you have another term.
another term, this one. Okay? So this is equal to, or asymptotic to, if you like, to minus plus 2 square root of x W prime. So this is an equation for W. Now, why okay, a few questions. First of all, is that equation solvable at x goes to infinity? What? Okay. Is this equation better than the area equation?
At infinity, no.
Okay, so in one sense, it is not better. It is not better because when x goes to infinity, we still have something that is not analytic. Okay, so it still have an irregular singular point at infinity. Still it is good because by trimming the most diverging terms, right, we expect now that all the terms of W will go to 0, maybe in a peculiar manner, but they will go to 0 at x goes to infinity. See? Okay. So now we have...
Are you hoping that they will go to 0 in that way? Or
they must be, because this is what I showed you in the last round. Good. So, this is an equation, and now we would like to solve it. Not to, solve is a strong word. We want to do something with it. Here is a red. Now where is the eraser? I just hope that I didn't make a mistake in the sign here. Let me make sure that, of course, I erased the calculation, so now you have to trust me. You have no other choice. Minus plus, yes. Okay, good. So, what I would like to do, note that if I didn't have this part at the right, that's why I have isolated it. Why I sent this to isolation? That's because what I can say about the left-hand side of this equation, if you see such an equation without the right-hand side,
it's an irregular singular point. You can develop a series.
Regular.
this is a solvable
The second type,
equation.
Rubinius.
This is a solvable equation because it's equidimensional, right? And for every equidimensional equation, you know that the substitution W is going like x to some power will solve it. You're not just going to. So instead of that, I would like now to guess an expression for W. I would like to write W as a sum from n equals 0 to infinity of an x to the alpha n. That's for free because I didn't specify anything, including alpha. And so what is the, okay, now what is W prime? W prime will be sum from n goes to 0 to infinity of alpha n times an times x to the alpha n minus 1. It's derivatives, and W double prime will be sum from n equals 0 to infinity of alpha n times alpha n minus 1 times an times x to the alpha n minus 2. Now, the nice thing here is that all these three terms are proportional to x to the alpha n minus 2. You see why?
Yes.
Okay? So what I will get from this is sum from n equals 0 to infinity of alpha n times alpha n minus 1 plus minus 1/2 alpha n plus 5/16, all that times an x to the alpha n minus 2 is equal to minus plus sum from n equals 0 to infinity of 2 alpha n an x to the alpha n minus 1/2. Can you understand that? This I claim that this and that are exactly the same. Okay, good. Now we want to solve this horrible thing, and to do that, we would like to. Okay, maybe I will. In this course, we'll get infinite black hole. Now, I can never deal with such problems without writing the first few terms. So please help me. What will be the first few terms of the left-hand side? Let's speak about n equals 0. What it will give me?
5/16.
Right? This will be 0, this will be 0. And I will get 5/16a0 x to the minus 2. What will be the next term? Please help. The 1, n equals 1.
Alpha minus 1.
To the alpha minus 2. Right? These are the first two terms. Okay. What are the first two terms of the right-hand side?
First one 0.
Okay. The n equals 0 term gave me what? 0. So what will be the n equals 1 term? Minus plus 2 alpha a1 times x to the n x to the alpha minus 1/2 minus plus 2 not 2 4 alpha a2 times x to the 2 alpha minus 1/2, and so on and so forth. Okay, now the point is that a naught, first of all, a naught must never vanish, and we can always take it to be, I mean, it's because, you know, it's a homogeneous equation. So we can always take a naught to be something, like 1. It shouldn't vanish, but it can, if it vanishes, then you can rearrange the series to have it not vanish. So a naught must not vanish. So if this must not vanish, we should find something on the other side that will have the same power, x to the minus 2. And this dictates that what? That alpha must be minus 3/2. Right? This implies that alpha must be minus 3/2. So what we have here is 5 over 16 A naught is equal to minus plus 3A1, that's plus minus 3A1. So we know that now A1 is 5 over 48 A naught. Right? Which makes sense because we discovered it before. The 5 over 48, if you remember, was the next term of the... So this is the same 5 over 48. And it's with the right power of x to the minus whatever. Okay? Now that we understood that and we dictate the value of alpha, right? Now let's go back to this equation and write the general relationship. So what we have here? We have minus 3/2 n times minus 3/2 n minus 1 plus 3/4 n plus 5 over 16. Right? This is the coefficient of all this, right? Times an will be equal to 2 or minus 3/2. So alpha is minus 3/2. So 2 times alpha. Okay. I have a minus plus. 2 times alpha is 3.
Minus 3.
Minus 3. So I have a plus minus 3 times a n plus times n plus 1 times a n plus 1. Right, and you can see that the powers here we have x to the minus 3/2 n minus 2, and here we have minus 3/2 n plus 1 minus 1/2. It's the same. So these are coefficients of the same power. What?
Why so it will be n plus 1?
Like here we got A0 is balanced by A1. We want the coefficient of the same power of x.
Oh, okay. No, because the sum starts from 1. Okay.
Same power of x. That's it. Okay? Can we make this expression a little bit more friendly to us? So what we have here is, I mean, we can take all the minuses from these two guys in the parentheses. So we have 9/4 times n squared. This is this and that. Right? Now the next term will be 3/2 n, but then we have 3/4 of n. So we have actually plus 9/4 of n. Just algebra. Plus 5 over 16 a n is equal to plus minus 3 n plus 1 a n plus 1. And now I would like to use the following guess. N plus 5, 6 times m plus 1, 6. Does it work? multiplied by 9 quarters. Is that true? I have n squared times 9 quarters. This is that. Right? I have 5/6n plus 1/6n. So it's n times 9 quarters. This is that. And 5/6 times 1/6 is 5 over 36. It's 5 over 36.
Okay.
And I have to multiply it by 9 quarters. So the 36 becomes 4, and 4 is 5 over 60. Yes.
Okay.
So this times an is equals to plus minus 3, n plus 1, a n plus 1. Good. So now we have the whole recursion relation for the W series that I wrote here. Okay? So the W series may be written as the W series is, okay, the recursion relation is a n plus 1 is plus minus 9 quarters n plus 5/6 times n plus 1/6 divided by n plus 1 times a n.
Should be
Yeah,
Yeah,
so
3,
those
4,
are
The 3, where is the 3? Downstairs. So
you can just make it
the
3
3 makes this one 3.
Yeah.
Okay, let's sanity check. A1, n equals 1, n equals 0. So A1, what it will be? It will be 3 quarters times 5/6 times 1/6. This is, again, this is 5 over 36. 36 divided by 3 is 12. And we have to multiply it by 4 is 48. So it's 5 over 48. And this is 1. So it's 5 over 48 times A0. It's only that we have to, here we have either the plus or the minus, depends on the sign of the
square.
of the asymptotic relation. I mean, of the controlling factor. Yeah. Okay. Good. So what's the answer? Now I want to figure out what is the general term. So let's assume that A0 is 1 or whatever, some constant. What will be AN? Okay, what will be AN if I have A0? Right, so I have A0. And you see what's happened. First of all, A1 is A0, and here I have 1. A2 will be A1, and here I will have 2.
Yeah, it's factorial.
It's factorial, again. Great. So I have, first of all, I have here n factorial. Thank you very much. Another thing, every step I have the 3 quarters. Right? So I have the 3 quarters to the power of n. I will write the A0 here. Okay? Now, what remains? So it's now I have to do the trick with the gamma functions. Right? So here I will have gamma of what? Of n plus, no, gamma of n plus 5/6 will start from, I have to add 1.
Yes, but this is n plus 1. So when you go to n, it's exactly what you want.
This is
plus
an now.
Yes. So you remove 1 and you add the same one, so you get gamma of n
okay.
plus 5 over 6.
5/6 gamma of n plus 1/6 divided by gamma of 5/6 gamma of 1/6 that will stop the recursive relationship, the recursion.
You need to add like plus minus 1 to the n.
Wait.
Actually,
5, 6, 1, 6. This is plus minus.
yes.
Here? Anything else? No. Just one piece of knowledge that you will be extremely happy to learn, which is that gamma of 5, 6, gamma of 1, 6 is 2 pi. So yeah, we can write it as 2 pi and get rid of it. Good, fantastic. So now we know that what is the answer? Okay, we have the complete answer. So y is asymptotic to what? To x to the minus 1/4, e to the plus minus 2/3 x to the 3/2 times sum from n equals 0 to infinity of plus minus 3/4 to the power of n times gamma of n plus 5, 6, gamma of n plus 1, 6 divided by 2 pi n factorial, and all this is multiplied by a0 or something, right, by a factor, because it's a homogeneous equation and I can always multiply it by whatever I like. Good. So this is the answer in all its glory.
You forgot the x.
Oh, sorry. That's it. X, of course, to the minus 3/2 and minus 1/2. Oh, nice. Plan ahead. Now I will do another mistake, right? Plus minus 3/4 to the power of n, gamma of n plus 5, 6, gamma of n plus 1, 6 divided by 2 pi times n factorial times x to the power of minus 3/2 n minus 1/2. Yeah.
Why you subtract 1/2? It's just
No, so you're right. Minus the half.
Should be
yeah.
Yes.
Yeah.
It was being the derivative.
Alpha n. That one. Okay, and at least you can see, regarding your question before, that all the corrections are coming in inverse powers of x, so they are going to 0 and x goes to infinity. Still the question is now, what I can do with this power series? Okay, what we can do with this power series? What will happen if I will take x equals 1, say, and I will start to sum the terms?
Before that you said that x equals 1, it's enough to approximate our function as it is.
Yeah, okay, but I have 2% error.
Okay.
So I want to use this power series to recover from the 2% error.
Okay.
What will happen if I will start with some value of x, or maybe x equals 1/2, right, if you like, x equals 0.1, and I will start calculating terms in this series in order to approximate better and better y.
I mean, math sometimes it's crazy because we said that x approached to infinity, but now we said, okay, let's take x equals
Oh,
1.
okay. Take x equals 10. I don't know what is close to infinity, but 10 to the 6.
Yeah, I see.
Sum I take that.
And you want to sum all these terms, right? Here is the problem. This series, because the law of conservation of difficulty, this series do not converge. Why? As I told you, at large n, gamma of n plus something is going like n factorial.
Yeah, we have n factorial in
At large n.
Yes.
At large n.
factorial
So, okay, so what I have?
Yes.
I have, now forget about signs, I only look for orders of magnitude. We have 3 x to the minus 3 halves over 4 to the power of n. This and that. Is that growing or decreasing as n increases?
Depends on x.
Depend on x, right?
Yeah.
The larger x is, the smaller is this term, and then we have an exponential decrease with n, right? So if x is such that this term is smaller than
Less
1,
yeah.
right? Then this term will decrease exponentially as n increases, right? So this gives me an exponential decrease. Then we have n factorial. So this gives me a factorial decrease. Who is stronger, exponential or factorial?
Factorial.
Factorial. However, here I have n factorial square as n goes to infinity. So one n factorial goes away. So I have a competition between the exponential decay and the factorial. Who is going to win? The factorial. So the terms are going to grow for every fixed x. For every fixed x, the terms in this series are going to grow eventually. Eventually they will grow. Of course, if I will take x equals 1000, okay, then I will get here a very small, let me take x from something that x equals 1,000,000, right? So square root of x is 1000, right? So x, this will be 3 divided by 4 times 10 to the 9.
Right.
Very small number. Okay? And then so it will be order 10 to the minus 9. And then I will multiply, I will raise it to the second power, it will be 10 to the minus 18. Very small number. And then I will raise it to third power, it will be 10 to the minus 27, right? But eventually, when n will become large enough, it will take over. So if I will look at the terms of this series, term by term, right? Term by term, this is an as a function of n. So if x is large, like as I told you, if x is 1,000,000, then I will get, the decrease will be much more pronounced. But eventually, then factorial wins. You see? Now, if I'm starting from x equals 1, so I have 3/4, okay? So 3/4 still, if I raise it to the power of 2, it's 9 divided by 16, and so on. It goes down. But the time it takes, the number of steps I will have to take until the n factorial will take over will be much shorter, right? So if this is for x equals 100, say, then for x equals 1, I will do tac, 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 and blah, blah. Right? And if I will take x equals 0.1, then it will go up from the beginning. Right? But if you forget about that, the larger x is, the more terms I have to go until it will start blowing up. Did you understand this? Because this is very important. But still, if we take n to infinity, then the series diverges.
So we take x to
N to infinity. for every fixed x,
Okay.
for every fixed x, if we take n to infinity, the series diverges. Good. So the question is, what I spent now like half an hour of your time on demonstrating you that we can write it like that, the Airy function, where this is a diverging series. Thank you very much, Nadav. You help us a lot. We have a diverging series. The answer is infinite. What should we do with this junk? Okay? Now, first of all, you have to understand that all the important series in physics are belonging to this equivalence class, right? Are diverging. Okay? All of them. There are physical reasons for that. So all of the series are diverging, and the question is, what we're supposed to do? What the hell are we supposed to do? What the hell are we supposed to do? And to understand that, we have to explain what we had meant when we put the asymptotic equal sign here. So this is something that we have to clarify. Welcome to the realm of asymptotic series. Right? So you are familiar from your first year to the series of the form y equals to sum from n equals 0 to infinity of a n x to the n. And when this series converges, like Taylor series, it implies that we can approach the right result, the correct result, with arbitrary accuracy by calculating more and more and more terms in this series, right? But you calculate the first term, second term, third term. If we calculate enough terms, we have a solution. Okay, so let's define Sn as sum from n equals 0 to n of a n x to the n. That's the first n terms, capital N terms. And what we know is that if the series is a Taylor series, then the limit as n goes to infinity of Sn is a series in the sense of first year, right? Partial sums, right? Is a series of the partial sums. But Sns are numbers, right? We know that this approaches y, the correct result. You see? So that y minus z approaches 0, whatever you do. Okay? This is another way to say it. It's the limit. As n goes to infinity of y minus Sn approaches 0. This is in regular series. Now what's happening in asymptotic series? A series sum from n goes to infinity, 0 to infinity, of a n x to the, it can be n, alpha n, for the moment, I mean, it may be not integer powers, right, whatever you like, is asymptotic to y, right? Don't confuse this y with the solution of the Airy function. This series is not asymptotic to the Airy function, it's asymptotic to the w, right? So this series, if you like, is asymptotic, this w, the series w, is asymptotic to y divided by x to the minus 1/4 times e to the plus minus 2/3 x to the 3/2, right? This is the function y that I regard to here, right? Not the I mean, asymptotic to W. Right? This is asymptotic to W if the following relation holds. First of all, everything is at x goes to x naught. In our case, x goes to infinity. I am not going to write it at every line. You have to please edit yourself. So, what I am going to say? I am going to say that the partial sum n minus W is negligible with respect to a n plus 1 x to the alpha n plus 1. That's the important thing. See? As x goes to infinity, the partial sum, the distance between the partial sum and the correct result, right, is negligible with respect to the next term in the series. This is an asymptotic series. As a definition of an asymptotic series. Okay, now you may ask, okay, but what's happened if I have calculated, I did the partial sum up to the 5th term, and it so happens that the 6th term is 0, but I have another term, right? In which case, this is not true. So if an plus 1 is incidentally 0, please replace it by the next non-zero term in the series. So by n plus 2 or n plus 3 or whatever, if there is such a, right, there must be, because otherwise it's not an asymptotic series. So this n plus 1 is if non-zero. And if it's 0, then take the n plus 2 or the n plus 3. Okay? Did you understand what I'm saying now? Good. That's it. That's it. So, what does it mean? How can I use this damn thing? Right? You see, the series itself do not converge. Right? It's only said that as x goes to infinity, in our case, every partial sum, the distance between every partial sum and the correct answer is negligible with respect to the next term. So what we can do, what's the simplest thing we can do? Suppose I have, yes, x equals 100. So it is these points. What should I do?
Find the minimum.
Find the minimum. Exactly. Find the point for which I did the, okay, let me change the picture. This one is the minimum. Right? So in order to get my best approximation to a function, and I have x equals 100, I should say, okay, this is the minimum point. This is 1, 2, 3, 4, 5, 6, 7, 10, 8. So try to approximate y by a naught x to the minus 1/4 e to the plus minus 2/3 x to the 3/2. Sum from n equals 0 to 1, 2, 3, 4, 5, 6, 7 of an x to the minus 3n over 2. See? This will give me the best approximation if x is 100. What happened if x is, let's tell you, if this is for, the black one, right? The black one is for x equals 1. What should I do?
The same. 3, 4. Find the minimum.
I should take 1, 2, and that's it. see? I have to find where is the minimum. Now, why there is a minimum? Because at first it is going exponentially down because of this term, and then when n is large enough, it is going exponentially up because of this term. So there is a point of balance, and I should take the terms up to this point. This method is called optimal truncation. We truncate the series at the optimal to get the optimal approximation.
יכול להגיד את זה בעברית גם?
optimal truncation? אין לזה מילה בעברית.
המילה השנייה אין?
אה?
אוקיי.
מכל המילים בעולם אתה מבקש את המושג שאין לי. חיתוך אופטימלי, כאילו זה יותר גרוע. יש פסוקים שהתרגום שלהם לאנגלית יותר מוצלח מהמקור. אבל מעט. Okay. Okay, fine. So this is the concept of asymptotic series. Again, I would like to stress that asymptotic series is the only thing you get in physics, right? So, okay, again, when you were taught, when they taught you quantum physics, right? They did show you perturbation expansion, right? In what context? They implement a perturbation expansion to what? To what physical problem?
מבנה הדק של אטום המידע.
Didn't they do it for Zeeman splitting?
Also, for both.
Zeeman effect, Stark effect, this was what, when I was a
Yes.
student, right? Zeeman effect, Stark effect, and the fine structure.
Yes.
Okay, good. So, what did they did in the fine structure? It was a 4x4 matrix,
Yeah.
right? So it's completely solvable. You don't have to do it perturbatively. You have a 4x4 matrix, right? It's not a big deal. Zeeman is also completely solvable. You can solve it completely. I mean, the fact that it required, they only want you to learn perturbative analysis. So the power series in the splitting of the hydrogen atom and in the Zeeman effect, these are converging power series. They don't have all these diseases. Why? Because the problem is solvable in the first place, and you don't need to do perturbative analysis. However, any real problem in which you have no solution and you have to do perturbative analysis, you end up with that. Right? Stark is even worse. Stark is diverging completely. But okay, but in any case you have to. So what we can do when we have we are going to end up with a asymptotic series. What we can do in asymptotic series, this is the simplest approach, optimal truncation. Of course, it tells you that the level of accuracy you can get is limited. You can't get more accuracy than this term. The value of this term, or the value of the minimal term at a given x. And the smaller x is, the farther away you are from the irregular singular point, the series is becoming worse and worse. Because you can get less and less term. Okay? Good. This is a asymptotic series. This is a method, the simplest method to deal with asymptotic series. We are going to learn much better method later during this course. Now, a few mathematical points about asymptotic series. Okay, maybe I will still use this whiteboard. Okay. First, Asymptotic series are unique, right? First, asymptotic series are unique in the sense that if I have y of x is asymptotic to the sum yes, something like that, asymptotic series. This is the asymptotic series of this function. There is no other asymptotic series that correspond to the same function. You see? So
By y you mean?
y is like any function,
Ah, okay.
and this is asymptotic series. Multiply by that, doesn't matter, right? And or w, y is w if you want, right? W is asymptotic to that. There is no other asymptotic series. Otherwise, what we did with making, when we calculate the w, we require the powers to be the same. This implies that it's unique.
You mean if we found asymptotic series?
It is unique.
Okay.
So if w or y, whatever, y, okay, w if you like, right? If w of x is represented by a asymptotic series, there is no other asymptotic series, right? You can't have, if somebody tells you that it also represented by bn x to the beta n, right? Then b must be equal to a, and alpha must be equal to beta. You see? That's uniqueness. On the other hand, asymptotic series are not unique. Why they are not unique? I say that there is only one arrow from, you see, these are functions. And these are series. So these are different series, and these are different functions, right? For every function, there is only one series. You can't have another arrow to another series, right? However, one series may have more than, right? If this is an asymptotic series, it can be the asymptotic series of this function and also the asymptotic series of this function. So the map between the function space and the asymptotic series space is what's the technical terms? One it's not one-to-one, right? It's I mean the mathematicians have names for it. What?
Not bijection.
Okay.
Yeah.
Whatever. Not unique, and it's not unique because if W is sum from n equals 0 to infinity of a n x to the alpha n, right? Then W plus let me describe it at, suppose that I'm speaking about something at x goes to 0, not at x goes to infinity, x goes to 0, right? Then W plus e to the minus 1 over x, a e to the minus 1 over x, is also asymptotic to the same asymptotic series.
Because the second term is negligible.
Because the
Then,
second term,
x goes to
as x goes to 0,
yeah.
is negligible and has no power series. So technically speaking, let me remind myself the right word. Yeah. Such a term, right, which as x goes to 0 gives you contribution, but it vanishes faster than any power, right, is called a subdominant term. And the non-uniqueness implies that every function plus a subdominant function will give you the same asymptotic series. So when we are implementing, for example, the technique of optimal truncation, we still have to pray. Why? Because we have to pray that the function we are trying to approximate do not have such a term, right, with a equals to 10 to the 9. Right? If you put a huge a here, and x is 1 over 100, I don't know, then maybe this is a large contribution. Okay? So this is a problem when we are using the asymptotic series with this method of optimal truncation. We have to hope or to wave our hands or to convince ourselves physically that we do not have horrible things like that, as you may know, appear in the theory of superconductivity and other branches of science. I mean, it's not that this is not a mathematical peculiarity that never happens in reality. Unfortunately, it does happen in reality.
How do you call second term sub?
What?
How do you call second term
subdominant? This is a subdominant. Subdominant. And that's I think. Right? So you have to hope that you don't have such. Okay, so if A is 1 and x is 0.1, yes, you don't see it, right? If you are close enough to the irregular singular point, this term will be negligible. But if you are a little bit further away and A is large, then it may be huge. Okay, third thing. Can we take derivatives or integrate asymptotic series term by term? Which means you see that if if W is asymptotic to a n x to the n, can I say that the integral over W dx is sum of a n the integral of x to the power of n?
For us to be able to do this, the sum need to uniformly converge, and here it doesn't even converge.
Okay, so some other smart mathematicians have to work on that, and there is something called Abelian theorem, A-B-E-L. Abel is the name of a person who showed that this is possible under some conditions that I am not familiar with. But just to let you know that you can integrate both sides of power series without giving it down, right? What about differentiation? Can I write that the W dx is d dx asymptotic to d dx of the sum of a n x to the n? Can I take derivative term by term? Now the general answer is no. Why not? For example, let's assume that y is asymptotic to x squared plus x sine x cubed at x goes to infinity. Right? Clearly, because this term is x times something between minus 1 and 1, okay, then the x squared is a dominant term. However, y prime will be, according to that, asymptotic to x plus x times the cosine of x cubed, but now we have to take the derivative of the x cubed, which will give us 3 x squared, so it will be x, we have an x cubed here, so of course this will be the dominant term. You see, so the derivative may take a subdominant term to become dominant. And that's why to taking the derivative is mathematically speaking prohibited. You can't assume that if you have an asymptotic series, then the derivative of a function is asymptotic to the derivative of the series by taking the derivative term by term. However, there are conditions that under which you can do that, right? If strictly speaking, if you don't have such ugly things, right? These conditions are defined in a theorem, a set of theorems by Tauber. It's Tauberian theorem. So there are abelian theorems for integration and Tauberian theorem for the differentiation. And in most of the physical problems, it so happens that you can take the derivative. Okay, but if you get into troubles with that, please refer the correct literature. So, okay. So what I would like to do now, however, I have only 1 minute. So, okay, so I will just show you an integral, tell you something about the guy who invented this integral, and the next lecture we will speak about the integral itself. So a very simple and intuitive way to understand asymptotic series you can gain by looking at Stieltjes integral. And now you want me to spell Stieltjes. Okay. I-E-L. This is Mr. Stieltjes integral. And Stieltjes integral is the integral from 0 to infinity of e to the minus t over 1 plus xt dt. So, next is the next lecture. I will tell you about this integral and its asymptotic series. But let me just mention that Thomas Stieltjes was a student in Leiden University in the Netherlands, and he was a very bad student. Actually, he failed the exams 3 times, and according to the laws of the Leiden University, should be kicked out from the university. However, he was a son of an influential politician, and his father talked to the right guys in the university and gave them a few offers that they cannot refuse. And as a result, he was appointed to be, he got some position in the observatory, in the telescope.
Sun.
What?
The sun.
The sun, yes. Thomas Stieltjes. He got he got a position in the observatory of Leiden University, and so you see what nepotism is working, and actually his contributions to science are enormous. I mean, he did tons of important works. Unfortunately, the one for which he is most famous for is the one that he didn't do. because still just while working in Leiden, he started a correspondence with Hermit. That was a person, not a polynomial, originally, right? With Hermit, and at some stage, Stieltjes wrote to Hermit that he have a proof to Fermat, to Riemann hypothesis. That at the time was, it was 1985, something like that. At the time, mathematicians have recognized that Riemann hypothesis is very important. So Stieltjes wrote a letter to Hermit saying that he did find a solution, a proof to Riemann hypothesis, and you know that the Riemann hypothesis is that all the zeros of the zeta function, all the non-trivial zeros, are living in the complex plane. This is the real x, and this is the imaginary part of x, are living at x equals 1/2 plus something times I. Right? Are living on the dashed line. All the zeros of the zeta function.
All the non-trivial zeros.
What?
All the non-trivial zeros.
Non-trivial zeros of the Riemann zeta function are living on this dashed line. And so Hermit was very excited, and wow, he wrote to Stieltjes, well, please send me the proof as fast as you can. And Stieltjes didn't do anything. He didn't send him any proof for a while. Okay, it takes week and months, maybe years. And Hermit decided to try a trick. And he talked to in the Paris they have this Academy of Science, and every year they pose a problem and they suggest a prize for the one that will solve the problem. So he told them, please, next year, pose a problem of proving the Riemann hypothesis, and he hoped that Stieltjes will try to get the prize and will send the proof. However, he already suspects that maybe Stieltjes do not have it. So he wanted them to the prize was given not to the proof for the Riemann hypothesis, because if they were deciding like that, nobody would have get the prize until today. Instead, they wanted them to show that there are no zeros to the right of one of this line, which is equivalent to some other to Gauss's to proof of Gauss's. I told you about it, right? Of Gauss, about the prime numbers, right? This is equivalent to the hypothesis, proving the hypothesis of Gauss that the number of prime numbers up to n is asymptotic to the integral from 1 to n of 1 over ln x dx. Right. As n goes to infinity. So okay. Anyhow, so they pose this problem, and after a few months they got the solution, but not from Stieltjes. Stieltjes never participated in all this story, and instead they got a solution from a student of Hermit named Adama. What? Adama. There is a quantum logic game that carries his name. Adama. So this was 1892, and Adamar sent not a complete proof, but a sketch of the proof, and he won the prize. And still just did many other things, but didn't prove the Gauss hypothesis about prime numbers that became the Gauss theorem about prime numbers when Adamar proved it. Now, it takes Adamar a few years to complete the proof because he got involved in another issue that was not other than the Dreyfus affair, because his cousin was Lucy Dreyfus, and at the time Dreyfus was arrested, and his family tried to help him. They were the only guys that believed in his innocence for a while, but okay, this is another story, but okay, that's
okay. Tov. So in this tutorial, we will talk specifically on irregular singular points. Do you remember what is irregular singular points, or I should remind you?
Okay, since we've done it with Snirab today.
Yeah, but I don't know. There is a Nadav's Snirab rule for students. It's right for undergrad students, but I'm not sure about graduate students. If the students ask for any background information and knowledge, he will deny any background that he has. How do I say that? He will say he didn't study that and didn't saw that, so the test will be easier because the lecturer will manage to do less material in the course. So that's what he told us in Introduction to Electromagnetism. So every time we said we didn't study something, he showed us and told us that for sure we will say we didn't study it. Okay. I think it's okay. Let's see. Yeah, it's working. Okay. Nice. So we can start. So everyone understand the basics of irregular singular points. What it means to have irregular singular point in OD? Yes? Okay. And when you have irregular singular point, what happens if you will try to do Frobenius series?
It will not work.
It will fail. Yeah. Because what do you need for Frobenius series? What?
Regular singular point.
Regular singular point, but okay. Yeah, I mean, it's zero order approximation, you need it to be like equidimensional OD, right? Everyone remembers that? Okay, nice. So let's start. We will start from a problem because everyone that is actually okay. We'll maybe give a little bit of a talk. We have one problem that is mandatory for that tutorial, and I prepare another problem from hydrodynamics that is very long. I don't think we will do it all. You can read it by yourself after class, everything. But it's very nice, and it's it will connect the material of irregular singular point to physics. Everyone is a physicist, so it's very nice. And I took that from theoretical hydrodynamics that is actually, I mean, magnetohydrodynamics, but it's close field to me. It's a field that close to what I do, so it's nice.
You can use it in plasma physics.
Yeah, what I'm doing is magnetohydrodynamics. It's in
Basically
plasma
the same.
physics. Yeah,
The same equation.
the principles are the same. Just need to add to the Navier-Stokes equation the magnetic field. Okay, so let's start from a nice problem. We will look on it. Question 1. We have an equation y2 prime equal to x to the third y. How it look like? What it remind you? Airy equation, airy and Berry. You saw also Berry, right? Okay, good. So what we will do, basically the same analysis, and then we will move to some physics problem. The first problem is find the irregular singular point of the ODE. Solution. What would be the solution to that? You say that for every real x, right, that will be continuous and we don't have any explosions. So the only thing that left us suspicious of the irregular singular point is the infinities, right? So let's check for positive x equal infinity, positive infinity, minus infinity is pretty much the same. You start to see it today probably on every function, right? Start to do the analysis for minus infinity.
No, we'll do it in the next lecture.
Okay, okay. So no problem. We will do it for x approach infinity. So what is the first thing that we need to do? To see that x approaching equal to infinity is a irregular singular point. What is the first step? Someone?
It's obvious.
Oh, it's obvious. I know that thing
Because-
explodes, but
I mean, because it's not a regular point, it's not a regular singular point.
but how do you check that something
Calculate
is?
the limit of this x squared times q of x.
Yeah, but
So
here you
it's
need to take the limit to infinity and you multiply by x. Okay, I mean, I catch your idea, but it's not fully formal. Okay, you need to take the limit to specific point. Define it at x0. X0
You can
where
do change of variable of 1
exactly,
over t and
exactly.
it will be the same.
So we will do change of variables. Z will be 1 over x. And everyone knows how to do that change of variables. I can write the final result of that equation.
Yeah.
Yeah? Okay, very good. Let's write it. It will be, and then 3 points. Then we get d squared y to dz squared plus 2 over z dy dz plus 1 over z to the 7th power y equals 0. Right? And now, if you assume that is regular singular point, that's for sure not ordinary point, right? It's not continuous at z equals 0. That's equivalent to say x equal infinity. but when we take the limit of z to 0 of z squared times 1 over z to the 7th power, the coefficient of y, right? We will get infinity. Infinity is not a rational number, right? So
It's not a number.
from that, x equal infinity is irregular singular point. So that is classic question for test. Find all behavior of all points of the ODE. You need to be suspicious and also be careful and look for the edges, right? X equal infinity and minus infinity are a little bit more tricky. You can see immediately why x equal to minus infinity is also a regular singular point. If someone will do any mistakes in calculations, well, he can end up with Euler-Cauchy equation here, because that will make sense. When you multiply it by z, it will be just constant, it will be 2. But here it will explode, and if someone will do mistaken calculation, that can cost him a lot of points. So be careful when you do that. Okay. So let's continue for the second part. The second part is find the behavior of the function. Find the behavior of y for x approaching infinity. Actually, what I mean in behavior, leading order, what is leading order? Did Nadav talk it?
The dominant. He called it the dominant.
He called it the dominant because it's S0.
Yeah.
The first approximation.
Yes.
The how
Others
that's called
are
optically
negligible.
thin. He talked about no, that is from the.
Optical truncation.
No. I'm confusing stuff. I mean, leading order is the order when you know the solution will look like y equal e to the sum over n of s and x, right?
Yeah, I showed that.
Yeah.
You saw that?
Here
And
we
the
talked
leading
about-
order,
Yes.
where do you cut that infinite sum? You cut that at the
then-
first n that will give you that x approaching infinity
Goes
goes to
to 0.
0.
Yeah, I showed that.
That is the meaning of leading order.
Mm.
Okay? That is a good question in a test, I think. If you're not sure what... Actually, you're supposed to know that at the test, but I don't think you will fail because of that thing. I don't think that is that crucial. That is just the technique. If you don't know how much times to repeat that technique. So
He called it controlling factor.
controlling factor.
Yeah.
Yeah, because that is the thing you will usually, because that is goes to 0,
Yeah.
you will have e to the Sn, and it's approximately what? 1 plus Sn. That's why, right?
If Sn goes to 0, right?
If Sn goes to 0, yeah.
You can.
For x is very large, you assume that you want to find the behavior of x approaching infinity. So what you actually have is this behavior, and that is actually very nice form. That means to find Sn, that's why you use after that multiply by Wx, because you know it will be much easier to work with given function times Wx than something to the exponent, right? Because this will give you a linear equation that we already discussed how to solve. And when you're doing something in the exponent, it will not be linear, right? But for this tutorial, because we want to find the leading order, you have to find Sn when to cut. In the case of, okay, taking enough terms until you get one term that goes to 0.
So you will ignore the W of x.
I will not do this step with W of x. If you have a little bit of intuition that is like airy, you will know when to multiply by W of x, right? So from now, by the way, from now, every ODE that you will solve, you will need some sort of intuition about the problem before you tackle it. Here you have intuition from airy. In other stuff, maybe you will have intuition from quantum mechanics. You know Schrödinger equation, so if it's second order differential equation, it can be familiar to you, right? And you will have some sort of intuition about the physics and the meaning of the solution, how it will go like. And you can always do dimensional analysis, for example, in that case, to find how it will explode. If that could be polynomial, you assume there is polynomial and you take the only highest order and you find like what we did in Frobenius, right? And the equidimensional. I think you're starting to get the idea of the course. Okay, so let's start. We talked a little bit too much. I talked a little bit too much. Okay, so to find the first order, what do? Substitute y equal e to the s, 0. And then you end up with an equation of s0 2 primes plus s0 prime squared equal x. How do you get that? That is just the second derivative of that thing, right? And that x, where before that everything were multiplied by e to the s, here there were also e to the s because of the form of the solution, actually x to the third. Yeah. And you end up with that equation after divide by e to the s 0. If I'm jumping too much steps, just tell me to slow down. Okay, so now we do some sort of an ansatz. What will be the ansatz? Can you guess?
What do you mean by ansatz?
Ansatz is something that you assume on differential equation. After that, if it's okay, it's not exactly ansatz, because at the end you will have to do some sort of sanity check that your assumption were right for x approaching infinity.
You just mean which of them is the controlling factor?
Yes,
When
exactly. Exactly, and you need to check yourself after that. So in our case, we know that s0 prime squared, we will assume that it's bigger, larger than s0 2 primes. At the end, we will have to check that, validate our assumption.
Nadav, just take all the three cases and check which of them is consistent with itself, and take the one that is consistent with
dominant
itself.
balance.
Yeah, we do the balance.
Yeah, dominant balance.
Yeah, but there is no formula for that. Sometimes you will need to do other assumptions.
Yes. So
I will try to give you nice examples in future homeworks that you will need to take, maybe in that example S02 primes.
Nadav, just check all the three cases and that's so.
Okay, I mean here you can, but if you add y2, y4 prime, that is a little bit more tricky. You will need
You can, but it
you will need to
be
do
much more-
something
Yes.
and see if it's working. If not, come back again and do the whole process again. Recommended to have some intuition what will work.
Oh, maybe you can take
There
the
is-
equation from the air equation.
What?
Maybe you can take the
Yeah,
equation from the air equation.
exactly. That's what I said. So, okay. Now we continue. We get that S0 is prime is what? Let's see. I think I have did not have mistakes in calculation. Let's see. No, I don't have mistakes in calculations. We take the square root and don't forget how many solutions there is to second order differential equation? Two solutions. That means
Plus,
you
minus.
cannot forget the plus minus. If it were x to the third, x0 prime to the third equal x to the third, what were the solution? You're supposed to have three solutions. All the angles, complex angles, right? With 120 degrees from each other, right? A recommended compact form of writing it, if you have z to the n, it's like solving that thing, equal r to the n. R to the n is just the function. Here it's two function, it could be 0. Just write it in your familiar form of e to the I 2 pi divided by n times k, where k could be any number between 0 to n minus 1. And that will be n solutions. Right? Do you agree with me? You understand why it's very compact to write it like this? Because you will not want to do all the algebra n times if you have an nth order differential equation. In our exam there were third order differential equation and everyone forgot except I think me and Doron about that you have that angle between the solution. So be careful. So x to the 3 divided by 2, then we get that S0 is in the form of plus minus 2/5 of x to the 5th over 2. What is the next step? Validate our assumption. Do you want me to do the validation? You just need to take the derivative here. Set S0 not squared divided by S0 2 primes divide by each other and take x to infinity. I'm sorry, the opposite, and see if it's equal to 0. Okay, if you do it the opposite, you need it to go to infinity, right? It's better to do it like how it goes to 0, because, for example, if the ratio is e to the x times sinus x, if the ratio is that, it will not approach anything. So one option is just doing absolute value. Okay, that is okay. And then it's a little bit tricky because it will be 0. Okay, it will not approach anything still. So just do 1 over that thing and you will get the ratio, right? Because now it will Okay, that is not good. Good example, but just take it to 0, because it can jump from minus infinity to infinity. That's what I meant. Okay, if there were other function, okay, you can write it after, but let's not worry about it. Okay, so next step. Okay, we go into now. Let's I make it slow. I can speed up if or I move. Okay, Dima, it's okay. So I will do it at that speed. Okay, now assuming that y is in the form of what? E to the s0 plus s1. By the way, if you find the width of the problem, you can write here. You know what is the width? Yeah. If there is some sort of width to the problem, that means you have a size of some constant that will go to 0 or something like that. The problem, it's nice sometimes to write it like that, but sometimes it could be even the width to the square root, but don't worry about it. Now just, if you see that, that can simplify a lot your calculations. And remember, you can call that thing S1, it will be equivalent, but sometimes it's nice because if you know nice size of the problem, you can just multiply it here and it will simplify your calculation by a lot. So it's very nice. Okay, so let's solve. Y equal e to the s0 s1. Now substitute. We have actually that equation, it's general. Can just substitute instead of s0 plus s1, and after simplification we will get s1 2 primes times 2s1 prime s0 prime plus s what?
S0 prime to the
Yeah,
power of
0 prime to the power of 2, and I think it will be equal to 0. Yes, equal to 0. But just
Yes.
I'm right. Well, it should not.
No,
It should
S1.
equal.
S1 prime to the square. S1 prime square, because the first one you used. No,
What?
you need both of them. You need both.
No, the thing is, you have x to the third power.
No, you forgot the term of
Wait,
S1 prime square.
I need to see that I'm not making a mistake.
In your brackets, you put S0
Okay.
prime plus S1 prime. So
I
just
don't need
equal-
that term because it's cancelling out with the x to the third term. I add here
But you need the
x0.
S1. You need the S1 prime square. And in
S1
this case,
prime.
you also need the S0 prime prime. And the S0
If-
double.
Okay, if you want S0 prime prime, prime
You need all of
prime,
them because you don't know,
okay,
you don't know
and
before which is the dominant.
so let's just wait, add that x to the third, but
Yes, and the
this and
last
this
term is-
cancelling out,
Yes, only those.
and
just
you
to
have-
make
yeah.
it clear, and
And now you need
with
to know which
some assumption and intuition, if you remember from every derivation. You can do pretty much the same. Most of the time it will be the same, but you will need to rely on your intuition. Sometimes if you didn't got two solutions or how many solutions you needed from the first order stuff, you will expect soon to get all of your results. So for example, if let's assume that I got only one solution, I will probably try at the start to look if something I can balance it with S1 prime squared. Okay, so I will get two solutions. Okay, do you understand me? Okay, so I will continue. Now I assume a lot of stuff. That pretty much I will throw, and wait, I will not throw it because that is given function, but I will throw S1 2 primes because, okay, I can say something that is not formal. I have already two solutions. If I'm keeping S1 2 primes, we'll have another two solutions, and then it's probably negligible.
Nadav just says that if S1 is negligible with respect to S0, so does the derivatives of both.
Again, what?
So if S1 is negligible with respect to S0, so does the derivatives of both of them.
Yeah.
It means
Okay.
S1
It's
prime is negligible to
yeah,
S1 prime,
yeah.
and for the double prime.
Sure. Yes. But maybe I can find arbitrary functions, but it's good rule that will contradict that. But I'm not sure. I think because it's infinitely continuous. Yes. Okay. Yeah, probably it's right. Okay. So let's neglect that stuff also, and that stuff also, and we're just left with that thing and that thing.
And again, it's an ansatz.
And again, it's ansatz that we need to validate at the end. Remember that now S0 is given function. So what we actually get is S1 prime equal to S0 2 primes with minus S0 2 primes divided by 2 S0 prime. That will be equal, let's use my powers to get that, minus 3/4 x to the minus 1. By the way, nice trick, I didn't know that in the tutorial notes, but it's a nice thing to remember. We will talk about it probably somewhere on the 6th lecture or something like that. Is y 2 primes equal to qx y if all the assumptions of the ansatz you made in Airy are valid for the asymptotics at x equal infinity. You need to validate what you did already. S0 will be integral of, I think it's plus minus q of x dx, and S1 will be just, I think, minus 4 ln q of x. Okay? Do you see how that thing we will get from that? Let's write it very quick. S1 of x equal to minus 3/4 ln x.
But you have wrong coefficient.
What?
You have wrong coefficient.
Where?
It's okay.
It's okay.
Yeah.
That is just nice thing to remember. Sometimes they expect you in the test to do the derivation of that. When I did it in Kessler exam, we can just use that. And if you remember the next term that is completely horrible, don't even try to remember that.
You mean S2?
S2 in that form.
It's horrible.
It's horrible, yes. So don't even try, but if all of the area assumptions are right, that is the form you will get, and the thing that is nice that it saves you some time, sometimes in exam. But if you have a whole question, 30 points on that thing, okay, please do the derivation. Okay. Of that. Yeah, you can assume, you need to say what is the assumption that you're doing. All the assumption, all the neglection that they did already, you need to write that exactly in the test. Otherwise you will not get any points. And you can ask Nadav if for equation like that, you can just say what is the answer that, so show that it's valid and do that thing. If I were the grader, for me it were okay, but you need to ask Nadav. Last year it were okay. Okay, so that were nice trick.
Can we use it in homework?
What?
Can we use it in homework?
I prefer, because that is the first homework, that you will not use that on that specific homework. I prefer it. But for next homeworks, for me it's fine. I need to ask Snurb if it's also okay with him, but for me it's fine. So you can use that. But you need to validate your assumption. If you did that shortcut, at least validate your assumption. Okay? Not say you can see that will be in order of x to the ta 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 ta, that will be in order of x to the ta 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 ta. It's easy. Show that limit. It's 2 lines. Okay? So we get S1, and the question is, do we need to take another term to find the leading behavior?
Yeah, you need to check at least that this
Yes.
term goes to 0.
What is S1? Is S1 goes to 0 when x goes to infinity?
No.
Exactly. So now we will do that. We did that also with Nadav
Yes.
on dairy.
Yes.
Do you want
Actually,
me?
just wrote the first 3 terms as one, and just solved.
And he did that with omega, the next term.
No, omega.
No,
He validated that S2 goes to 0 at infinity,
yes,
and then
yes.
did with omega because it's much easier.
Yeah.
By the way, that's how you solve harmonic oscillator. You do exactly that thing, and in the end you search for, you try to find some leading term because you get some sort of equidimensional equation, exactly like Frobenius, what you did, and then solve it from then. And because of normalization and all of those stuff, that will need to be a finite polynomial, right? It can be a power series, and that's how you find the solutions of harmonic oscillator. But back then you didn't know what you were doing. You just look at the professor and you say, "Oh, that is a very smart guy." That is the thing he hidden from you. That is the mathematics that were behind and the logic. In the homeworks, I gave you to take 2 potentials and 2 points, that at least one need to be a regular singular point for a Schrödinger equation, and solve it. It's very nice homework. And find approximately with boundaries condition that you set, the energies level. So it's very nice, I think. So it's very cool, and then you can compare, for example, do it for harmonic oscillators, very classical example, and look at it and the energies level you will get for example, I think you will need to go until S1, and you will get some energies level, and you can compare it to the known harmonics oscillator energies level. That is very nice. So let's continue to S2. Do you want me to do that? I can continue, or we will move to the hydrodynamics problem.
Maybe just do the calculation until you neglect all the terms. And
Okay.
I think we can finish it.
Let's.
Good luck.
Yeah, it's need to find it.
Just write all the terms. It will be a lot, but you can just do it.
Yeah. I was so lazy,
Yes.
so I didn't even write the terms. I just wrote the validation for the terms I neglected in the tutorial notes. So I can write this, the final result pretty much after neglection, or we will do it. Oh no, I wrote that. Okay. So let's write that horrible stuff. Okay, so S0 2 primes plus S1 2 primes plus S2 2 primes, 2 not 3. And that is a relief. And from here we have just prime of everything here, so it will look like S0 prime squared plus S1 prime squared plus S2 prime squared plus 2S0 prime S1 prime plus 2S1 prime S2 prime plus 2S0 prime S2 prime equal to x to the third. If you don't remember the, let's say, binomial expansion of couple of variables until something like first order, that is the time to remember it. Quick, nice way to remember the coefficients is by Pascal's triangle: 1, 1, 1, 2, 1, 1, 3, 3, 1, and the other one is 1, 4, 6, 4, 1. You know Pascal's triangle?
Yeah.
It's a very nice way to remember the coefficients and put minus signs and all of that if needed at the right terms. Okay, so now neglecting all the stuff, and after plug-in, you know that this term vanish with what? With that thing, because that is the balancing we did already.
Yes, the S0.
That were S1, that is not legal. That is actually one of the things that I think we will say. Not yes.
What?
Okay.
No.
S0 with that. Okay, wait.
No. Yeah.
S0 prime squared with that.
Yes.
Now we are left with 2 S0 prime, S2 prime, and that thing. Okay, we know that S0 should be much bigger. Yeah, I'm right. Just checking that not wrong. Yeah, I'm right. S0 prime, intuitively, okay, we know that is much bigger than S1 prime, because we already know what is S1.
Yes.
So we can just say that is negligible compared to that.
Also there is
Actually, what we did here is not ansatz. You can just take the term out of S2 prime and see that thing is negligible. And from here we have, okay, so let's write the equation. We have S1 2 primes plus S2 2 primes plus S1 prime squared plus S2 prime squared plus 2S0 S2 prime. That is also prime. Okay. So what we can do from here? Any guess? What we will throw?
S2 double prime.
S2 double prime and S2 prime squared.
And S2 prime squared.
Yes.
Exactly. Exactly, because they are negligible as compared to S. That thing is bigger than that. That is some sort of an ansatz. And that thing will be bigger than that. That is also some sort of ansatz. You need to validate that at the end, but everyone, if you're here, you probably passed Math of Field Assist 1, so you should be fine at doing that at home. Okay, so let's write S2 prime equal to S0 at the numerator, S1 2 prime plus S1 prime squared. And I think we can probably, we know what is here, what is bigger, or what were the order of that? No, they're on the same order, so okay, we cannot do that. But I will tell you what is the final result on that. Let's see. Minus plus 21 divided by 32. X to the what? Let's see. Minus 7.5. Horrible. But always, if I remember right, when you have the equation y2 primes equal qy, you have 32 comes naturally to the equation. So don't worry if you have divide by big number, because it's already in the equation. Should be in the equation.
Can you calculate now S3?
I saw that in Wikipedia and it took me 1 minute to scroll down.
Wow.
So don't even try.
No, I want you to try.
Don't worry, in the homeworks I gave you, give a nice way to solve that thing. There is asymptotically. Give some sort of an idea how to solve that. There is a way to do that. That is not exactly right, but there is a way. But I gave on that a lot of points. So if you did that, you probably will have 100 in that homework. So it's nice. Okay, from here it's easy. You see that if we integrate, it's also decreasing. And then, yay, we found the leading order. You understand why I cried when I will need to go to S3 at my exam on third order differential equation? Okay, that was just simplest case that Nadav wanted me to do with you. Now we can do real stuff. That is the time. Yeah, I have time. So everyone remember things from wave course? a little bit. Linearizing differential equation. Do you remember from wave course? That is not the material for this section of the course. Okay, all the linearizing is non-formal for our course, but it's formal in wave course. Then you end up with very nice equations. And we write the first equations and what you get after linearizing them, and then we will get the ODE we want. Okay? So let's describe the physics at first. Okay, I will clean that word also. By the way, how was the last homework? Okay. I heard from you, but tell that usually not cry. Okay, Oz?
I don't think anyone here will accept with him, except for himself and you.
The only thing that is funny that mostly I'm comparing my homework with your homework in most of my undergrad studies, and then I'm calling you crying. So it's a little bit funny and not right to do so. I'm sorry.
The best thing that it's recorded.
Yeah, it's recorded. But I didn't copy it from you in quantum mechanics. But I'm usually solving the equations and the problems and then comparing myself with you. And for this year, I'm not taking that much courses. Okay, so let's get to the hydrodynamical problem. Let's at first start from describing the physical system. Equation is in the topic of hydrodynamics. I know most of you are not familiar with that, but that is okay. You just need to accept one thing, that is Navier-Stokes equation, and from that we will continue. Okay, so the problem is like that. Every classic problem in hydrodynamics talk about pipes. Okay? So for our case, because hydrodynamics equations are horrible, usually, and we want interesting stuff, so at least we need 2 dimensions. But we will not touch 3 dimensions because it makes calculation much horrible, but not add that much in our case. So we will look on 2D pipe, that the pipe that is y equals 0, and let's say here we have that is the y-axis, and that is the x-axis. The radius of the pipe is h, and we assume it's very large. When I mean radius, it's just the width divided by 2. Okay, so from here it's also h. For this thing, if you will solve Navier-Stokes equations, that I will write immediately on the board, but let's just assume that we know how to solve it. We solved it already for zero solver. That is not interesting at all, I promise you. And when I did the wave course, we derived that. It will be only depend on y, because you have flow there, and to be here and x, and here and x, you don't have any difference, so you will not expect any dependency on x. But the flow u means capital U, I mean vector, Okay, capital will be now a vector. So it will go like u max, the max velocity, 1 minus y divided by h squared, like that. That is an approximation. If you heard about it, if you look on a profile of the velocity, it will be parabolic. I mean, the velocity here will be with respect to the y. When y will be very close to h, it will be very small. When y is very close to 0, it will be maximal. It makes sense. Why? Why physically it makes sense? Assume there is viscosity, it's a hint. Because then the most interactions come from the boundary, right? So here you have less friction, and here you have more friction, right? So that's how the profile will look like. Okay? Everyone agree with me? I think actually, no, that's come from Navier-Stokes equation. Okay. The thing that we will have the interest on in see how the flow is going here. That is just 0th order approximation. Here, let's say at the layer that is very close to the boundary, we know that u will be 0, but that means that u prime is, u1 will be the dominant, because here u0 is pretty much 0. But that is not with y equal h, but let's call that around yc. Okay? So for yc, u0 of yc is pretty much equal to 0, but you get the idea. Okay, that's for the picture of the physical problem. Now let's get to our context. The thing is, how do you approach any hydrodynamical problem? Navier-Stokes equation. That's the equation that describes everything, and we didn't manage to solve them without any approximations. So, by the way, that is PDEs. You know what is PDE? Partial differential equation, exactly. So that is actually outside of our material of the course until we will get it inside to our material. Okay? So I think actually Nadav gave in the past in the test PDEs because you're already a graduate student, so we assume you are familiar with the equation of PDEs, but okay, we get the idea. Another one, divergence of the pressure, gradient of the pressure, plus mu. Mu is the viscosity coefficient, Laplacian of u. When I'm doing Laplacian on u, I mean Laplacian on ux, uy, uz, not doing, you understand. Laplacian gets scalar function, and that's got. Here I should not use u, use capital V, or V with vector, but I already wrote that, so let's stick to u. Understand that this thing is two equations because it's vectorial. And the other thing, that is something that you assume almost we don't know a lot about compressible fluids. So the equations just get nasty. Most of the research in compressible fluids when it gets relativistic. So when it gets relativistic, you have very fast particle, therefore sometimes it can compress. So that will be horrible. But for incompressible, you have something that you get from the continuity equation, is that the divergence of u equal to 0. And we also see that in electromagnetism course, the advanced one, but you see that also in waves, right? In the classic wave course.
Yeah, but it's only in the case that you use stationary.
What?
It's the only
No,
indicator.
it's not for stationary.
Why?
Why it's not for you stationary? Why it can depend on time?
You mentioned the.
Let's wait.
It's have to be.
Oh, okay, we can talk about it later.
Okay.
I can look on the derivation of that, but I think it's just the.
You mentioned continuous equation and it should be partial derivative of y with
I
respect
know
to t.
how the continuity equation goes like. What I'm saying is one of. Okay, if you meant that that thing,
Yeah.
the complete derivative of rho will be 0.
Substantial derivative. They're called.
Substantial is not 0. It not has to be 0. Because when you have zero, okay, a little bit, that is not our material for the course, that is material for course in hydrodynamics. But let's just try this. From some sort of chain rule that's called Eulerian frame of reference, you get that thing, and if that thing equal to 0, that thing will be equal to 0 only if that thing will equal to 0. There is no reason for that to be equal to 0. I don't want to talk about that. If you want to continue discuss on that, we can do it later. Okay, because we don't have much time and want to get to the ODE and start to solve it. From here, what we will do, we assume we have stable solution. I already provided you with the solution to U, but we also need some constant pressure and some perturbation to the constant pressure, because you need, when it's laminar and it's very beautiful, that the nicest case, assuming that pressure is constant, is pretty much, it makes sense, right? You know what is laminar flow? A little bit? It's flow that has a lot of order in it. That's the intuition I will give you. You will not have a lot of eddies and things like that. You will have nice flow, and I recommend you to, after what we do, look on a video of laminar flow. The water will look to you steady. So it makes sense from your physical intuition that the pressure will be constant. If it looks steady, okay, it makes sense, right?
The second equation is about laminar. Yes?
What?
The second equation actually means that flow is laminar.
That
Right.
means incompressible,
Yeah, but
not laminar. Laminar, no.
I mean,
Laminar, the exact definition of laminar comes from Reynolds number, if you know what is that.
yes, but
And it's the definition, I think it's for Reynolds number that is between 0 to 2000.
this equation is the same like in electromagnetism for magnetic field. It's based
No.
from Maxwell equation. It's the same. Like
It's not linear.
divergence of B, it's equals to 0. It's one of the Maxwell's equations.
Oh, okay.
I mean
If you
that-
want to look
So
on that,
and actually this means that there is no magnetic
Monopole.
charge. Yes, and the
I-
line of magnetic fields are straight. So basically this.
But
this
for
means
your
that-
intuition, you also use all the other Maxwell equations. That is not right in our case. Okay. Okay, you can read a little bit. Something that nice is on streamlines. Okay, read about it later. I want to continue. Okay, so the thing we know we have stable flow laminar in all of that pipe. We want to do some perturbation on ux, uy, and p, and we assume all perturbation are in the form of f of y. They will only depend on y because you have symmetry in the x-axis, right? And the other thing is, let's write that as fy tilde times e to the I. I chose alpha because that's how it's written in the literature, but you can write k. That is just the wave number. Just assuming the perturbation is a wave and see how it develops. Usually that leads to the dispersion relation, right? Alpha and omega can be complex numbers, so it could increase and decrease with length and time, right? There is no reason that alpha will be complex because you have symmetry in x, but because we're dealing with something that a little bit, we assume a small perturbation, we actually gave a little bit of break in symmetry here, if you can see it. Because now not all points are equal to each other. You see?
If alpha is complex, it means that
We have
it will
also
die.
dependency on x.
it will
That's what
die
I mean.
if alpha is.
Yeah. It's complex, it could be dump or
Yeah.
exploding.
Yeah.
Yeah. But we know exploding is not physical, but we assume a little bit of perturbation. That means if you have the exploding term, that means, okay, the flow is not stable, and then we will just break and everything will break. So with that assumption, you plug it in and you get all of the equation. I wrote it very nicely in the tutorial notes. You will reach an equation, very, very nice equation, that's called Orr-Zumberfeld equation. For now, we didn't assume anything about where we are inside the pipe, right? I will just write Orr-Zumberfeld equation. We will use d for d to dx, just because it's easier for me and I'm lazy. Okay? You also use that d in QFT, so let's feel a little bit cool. Okay, because it's nice. I will take my computer and write it, because it's, maybe I will need to, I need some space. D squared minus alpha squared. Let's call the V. Okay, V is the perturbation in the velocity in the y-axis. Okay. Oh, and here it's not the x, it's the y, because the dependency is only on y. So what we get, that equal to I alpha r, which is called Reynolds number. It comes from the equation, and it's equal to u max h divided by nu. Okay? And u y minus c. C is just omega divided by alpha. It's the wave phase velocity. You remember it from wave course? Okay, nice. And now times d squared minus alpha squared v minus I alpha r u2 primes y v. Okay, that is the equation. What is the order of that equation?
4.
4, exactly. Because here we have the squared and we have the fourth derivative. Oh my god. That is way too much, but after some neglection and okay, we will explain what is the things and we will just jump to the final equation. Okay? And the thing here is we now assume our position in the pipe. That is completely general to describe the pipe and how a perturbation in the laminar flow, because we know there is perturbation here, but that could be also a finger or something like if that pipe can model wind tunnel and the airplane that glide on it, that could be the airplane that interacts with the wind tunnel, right? So that can model a lot of stuff. That equation is completely general. And you see, for undergrad, you always end up with second order differential equation. But now when we are a graduate student, we see our Zumberfeld equation, and unless you took hydrodynamics course, and we end up with 4 derivative. And now it's the time to introduce the physical, the physics of our case. We need that. That means we can assume something very nice on U. One thing, because the pipe, we assume it's very wide, what will be the second derivative? Very small, because it will be in order of, it will be O of 1 over h squared. So it's pretty much 0. So it's very nice to take it to what? First order approximation. It's a little bit funny because it's parabola first order approximation, so we all know how it will look like. But let's say y, and we develop it around yc. Yc is just arbitrary point that near the edge. We will get u0, that is, don't think we even need to neglect it. I think I neglect it and throw it to 0. I think I said it equal approximately to C or something, because okay, the thing here, you're with me? U0, the 0 approximation, will be approximately, now we introduce the velocity of the perturbation, it will be approximately that. Why I'm doing that I will not explain, but there is physics behind that, but agree with me. And we add the first order perturbation, y minus yc. I'll agree with that. We are fine, a little bit. Okay, I'm fine. And the other stuff I just throw because it's plus O of 1 over h squared. So it's extremely negligible. That is in the order of 1 over h, that is okay to keep. But actually times y minus yc, we are modeling that here, but it will still not be in the order of 1 over h squared, because it's actually something here. It's very close to that, but it's not that close. It's a little bit far. Okay? we want to see, because here, very close, it's not interesting. You have pretty much zero velocity. But here it's very interesting, because here there is a lot of eddies that start to develop, and the instability start to really shine. Or explode. But shine. Let's call it like that. And from choosing some unitless or something like that coordinates of the problem, we will call that eta, still alpha r u prime 0, let's call that, to the third y minus yc. We end up from that with equation that is very simple. D eta to the fourth, because we had fourth order, we throw a lot of stuff, and we get times v, let's call that capital V, equal to I eta d eta squared v.
So you basically change the y
I
axis
basically
to
change-
eta axis?
I basically wrote that in the, I think it's unitless. Yes, I think it's unitless.
Okay.
If you know when you
I don't want
put
to check it.
what?
I don't want to check it. If it's unitless, I just believe it.
Yeah, I think it's unitless. You can check that, but that is just simplify the end result after neglecting some of the terms. So let's write that. That equation. Does it look familiar to you? That equation? Galinsky.
Fortunately, yes.
This one.
Yes, yes.
So actually, if we will reduce the order of that equation, let's call that phi. Let's write it like that, d square v. What we will get? Some sort of Airy equation. So we will get phi 2 prime equal to I eta phi. So it's actually very familiar, right? Okay, I mean, we will need to do a little bit of stuff around it, and we will get. You missed the highlight of that.
No, you haven't missed anything.
We just said, okay, after doing all of that, we get that equation that looks very familiar, because if you reduce the order of that equation, what you will end up is with that equation. So it's very nice, because it looks very similar to the Aryan-Berry equations. From here, you know how to solve that, and that will be very nice. You will get some sort of equation, and if you remember, because you have the I and you do square root of stuff, you will actually get something that approximately to E, the leading, or not the leading, the zero order, the dominant behavior will be something like E, let's write that as X, to the E of plus minus I pi over 4 X to, it's 3/3, 3 halves,
What?
right?
You have an exponent of an exponent? Ah, okay. So
Yeah, it's because of the I.
yeah, no,
You
just
know
can't
the
see-
derivation
No,
of.
you just wrote, so I couldn't see the full. Power
I
of the
think
exponent.
it's something like that. If you remember the thing I did with the Q, so you can do it like that, and now you can just take the integral twice and you got the zero order behavior. So it's very cool, but okay, I need to change that to eta. It's very cool. That is the asymptotic, by the way, when eta goes to infinity. It's a little bit strange because eta will look to you like 0 because you have coefficients like u0 prime that will be in the order of 1 over h, and y minus yc that will be very small. But if we will, to make it interesting, assume that Reynolds number is very, very big. Reynolds number is something that quantifies how turbulent the flow is. We will want to look on extreme cases. So we can actually talk about eta will equal to approach infinity. It will be something like I told you here. Close, but not that close. So we start to develop a lot of eddies. מערבולות, למי ש... So it's very nice, but we need to do 2 integrals. So that is very bad. That is not count for final answer in our exam. Unless you will do some asymptotics on the integral and all of those stuff, and that will be horrible. So actually it looks very familiar. You will want to do that thing and end up with a nice solution. It will be very quick, but you actually end up have to, for finding the leading behavior, we will need to solve, where is that? That 4th order differential equation. We will need to do all of that on that without reducing the order. So it's sad, I know, but okay. Ozzy, you're looking not happy. No one happy when you see that equation. Okay, if you're very creative, you know you know that function, and it will be now non-homogeneous 2-order differential equation. I mean, you can still play with it and do perturbation now again on that thing, because you have that and that, but I didn't thought about that when I wrote the tutorial, and actually it's a very nice example to show what to do when you have higher order differential equations. So pretty much horrible. I will do the first 0th order, and if you want you can continue reading on it. I posted the tutorial notes and you continue read how to do the 1st order, and I try to write the intuition of what I'm neglecting, and you can try to do it before and then see on the tutorial, because that is very extreme case. In my exam we were the first time that higher than 2-order differential equation appeared in test, so everyone just freaked out and forgot a lot of stuff.
You are not
Yes.
writing the exams, right?
No, hopefully not.
So it's okay.
No. Just don't tell Snap to ask Kessler what to put in. He's a very nice lecturer, but his exam sometimes he finds somehow how to invent himself each time. So yeah. Okay. So let's first write. Trying to find. Where is that? Okay. Let's first. I calculated at home the 4th order derivative of v with respect to eta. Okay. The derivation I'm doing now, I didn't find in any classical textbook. They usually don't know that method, but it's actually, I think, presenting the real power of that thing. Because now you can get a very good approximation that will be completely analytically, and that will catch all the behavior of the problem and every physical thing that you will need from that problem. So it's very nice, in my opinion. So it goes like that to 4. I will stop writing derivatives above 2 with primes because I will not finish writing everything. And S3, 0, 3, S0, 2 prime squared plus 6. I think I did at 1 AM last night until second order of that thing. I find S2, and I will tell you, it were better than some of our equation in the homework last year. So don't worry, I will not put any equation like anything like that in the homework. I don't want to torture you, unless you are Kalinsky.
You should have anticipated that.
But even Kalinsky should not do that, right? That is way too much.
Yes, that's you should do.
Maybe. Okay. And the second order, we just write that thing. We divide already by e to the S0.
The opening brackets and the ending of the brackets are different.
That is only in your world, Kalinsky. I'm imagining that. Okay, and that equals to I eta S0 2 primes plus S0 prime squared equal to that. Now, what you neglect? So pretty much, look, that is very nice. All the last half of the hour we're just playing and explaining physics. Now we can really tackle a physical case and have maybe better intuition of what you neglect. So what do you need to neglect at first? Okay, I mean that thing is like dividing by eta to the fourth. Okay, that is negligible for sure, right? We did that thing, we have the intuition from that thing, so we know that take the derivative 4 times will just be negligible. Okay, so next one also we have s to the third. I don't want to hear about it. Okay, and now I have x s0 2 primes. Okay, maybe no, we don't want to hear about it. I think also that thing is very small to compare to that, because that is only first derivative, and we want to catch some exponent polynomial, rational polynomial behavior, and I don't think it will be negative, because here we got non-negative, so I have the intuition to do that. And here also that will be that 2 prime will be negligible if compared to that, and we will also have the cancellation, so whoever made that problem, if that appear on test, probably want to divide by it. So by the way, why I can divide by S0 prime? Because if S0 prime is 0, okay, assume I got that, that is pretty much like saying the solution will be constant. That doesn't mean anything. Okay, maybe for some equation it is the right thing, but for our case we know it should not be problematic. It's not constant. That is the thing we want to get rid of. Okay. So after all of that ansatz, you need to clarify at the end, and that is very tedious. I did that. Because, okay, that is the first tutorial about that ISP, so I have to write that. But in next tutorials, notes, I will probably say, okay, from here you know how to do that. I mean, it's easy, right? S0 prime squared equal to I eta, and then we got what we expected. It actually showed that S0 prime is equal to e to the plus minus pi over 4 I first eta to the half, and from it just S0 is 2/3 of e to the minus plus pi I divide by 4 eta to the 3/2. Very nice. So actually there is nothing that explodes faster, or I don't want to say there is nothing that also explodes, but that is the leading behavior over here. So it's very nice. Everyone understand how we got there?
Yeah. But you have like 4-order differential equation. Those are 2 solutions.
Right.
What happened to the other 2?
The other 2, let me think. I think they came in next orders. I got also plus minus.
Ah, okay.
Yeah,
And
now I
then the second
remember.
plus minus?
It was horrible. I got plus minus in other exponent that were. Yeah, that doesn't depends on that, and you have a lot of some sort of different waving of that, and that actually makes sense because you have 2 symmetrical waves that can propagate in that direction, if you agree with me, because it's 2-dimensional, and you have the waves that get back from the edge. So that is actually, now when I'm telling you, you will expect that differential equation to be on 4th order, right?
Yeah.
And by the way, v is the velocity to hit the boundary. How do I get the velocity of moving near the boundary? Exactly from the continuity equation, let's be correct, the incompressible, because you get du dx plus, it's just the perturbation, dv dy equal to 0, but we assume that equation will depend on x because that's some sort of the ansatz of the perturbation. So it will be just I alpha u with tilde plus the derivative of y v tilde that we know, right? And from that you just need to divide by I alpha and you get u. So that's it. I think that is a good place to stop. I think that is very nice. You can pretty much have the intuition of one where area appears. It appears almost everywhere. That is actually one of the surprises I had. I remember when I studied, I saw area function before. That where I saw that before. And yeah, it's very nice, I think. You don't have a lot of examples for it, or the differential equation that is not in your test. So, one more thing, another place that we will actually see in the course that area appears is near a turning point, but don't tell Snap that I told you already, okay?
We're
You know
sending
that-
the link to the meeting.
What?
We're sending the recording.
Okay, nice. You know that psi 2 primes from Schrödinger time independent equation proportional to e minus v of x psi, right? If you're a turning point that you turn around classically, v is approximately at 0th order equal to e, but the first order will be equal to x minus x0. So with shifting the equation, you actually get Schrodinger equation around the turning point. The interaction is actually modeled with every function. Okay, so it's very nice. You see that around boundary layers, when you have some stability and you want to look about the instability or something like that, every function appears a lot. That is very nice, and not a lot of people know about that, and there are professors that don't know this stuff. I don't know. That for me, when I found out, I saw error in a lot of places because my research is in instabilities. We finished, by the way. היה בסדר? נחמד?
ממש נחמד.
כן.
היה גיהנום האלגברה.
כן, לא, אבל חסכתי מכם.
כן.
כאילו, זה אלגברה מוכרת. זה אלגברה מוכרת, אבל אחר כך תחשוב מה זה, להציב פה עכשיו את S0 ועוד S1, אתה מתפחלץ מזה מהר מאוד.
לא הייתי עושה את זה במבחן, הייתי אומר אני אדלג על זה, ירד כמה שירד, הייתי גם רושם את זה.
ירד כמה שירד.
ירד כמה שירד.
אלא אם היית סקרן לדעת איך זה מתנהג הידרודינמית, כי האמת שהתנהגות הבאה באופן לא מפתיע, או שזה כן מפתיע, זה קבוע חלקי 4, קבוע טבעי. חלקי 4 קומפלקסי וזה.
הסדר הבא הוא
שזה
לוגריתמי?
כן, והסדר אחר כך הוא שוב פעם יורד לאיזה מינוס 7 חלקי 3, וזה ממש נחמד, כי אז זה אומר שזה תפס את כל הפיזיקה של הבעיה. אוקיי, the next term is like that, I forgot, sorry, דימה. The next term is like that, and the other terms goes like eta to the minus 7/3. So I actually know that the second term is vanishing. You also have that in your intuition because that looks like every equation. And then I know I can just cut it on the on S1 on the first correction.